spin is actually incoherent, it's random. So in spintronics, what you're doing is you're controlling the spin of the device, and from that we've been able to make different types of emitters that, rather than giving random light, can give out polarized light. And there's certain reasons why you may need that. We've also used these nitride-based devices for neutron detection. We've been putting into these, and this is always a journey. We've been putting in transition metals, which normally made material that was very resistive, which is not good if you want to pass a current through something. You can then go to rare earth materials such as the gadolinium. But gadolinium also has the largest cross section for thermal neutron detection. So we then got in and did some work on neutron detection. You know, part of this is just also to show that you can have a journey in working your way through different types of materials and problems. And when people say they have a research expertise, if they stay in that, then it isn't really research. So I tell people I have a research expertise, but my expertise is research. It's that ability to be able to move in and through different problems. I think one of the next areas is going to be multifunctional devices. So optoelectronics is where you're modulating and changing between the electrical and optical properties. EMO devices is actually the ability to be able to put in magnetic fields into this as well. So that was just a little bit of background of some of the work that we've done in general. Just now I'm focusing on spintronic works, and I think Renevy, I've got one of my students who's doing some work in that area, who's joined us this morning. Some solar, and then I also have interest in some other areas as well. So why are we interested in solar? It's really about the ability to be able to capture sunlight and to generate electricity from sunlight. So solar is great. There's a number of different ways to do this. Photovoltaics, what we're going to talk about today. Solar collectors, so you'll see these things where they take mirrors and focus them onto a point. Solar thermal, where you warm up things and cycle it through something. And passive solar, you know, certainly in colder climates, you can design houses where they can actually trap the heat during the day. So why are we interested in this? You know, America does have some parts that are warmer. We're now in the Atlanta area over here, which I won't bring up that. But this gives you an idea of just how much power you can have on a solar panel in one day. My belief is that over time, as we move away from oil-based energy systems, we're most likely to move towards solar for most things. So you're going to see these areas becoming our generation hubs for the whole of the country, and nuclear, where you can't really have a grid where it hits well. I think the issue is, and there's something here which people find you know, really quite amazing, is, and this is older data, and I still need to update this a little bit, but you know, what's really interesting about this is America uses about 1/20th of the world's energy. This is energy, this is our current energy trends. So this quadrillion BTU is British thermal units. So America uses about 1/20th of the world's energy, about 20% of the world's energy, for about 1/20th of the world, for about 1/20th of the world's population. So you can see here, about 100 quadrillion BTU. If you then look at how this energy is generated, things like petroleum, that's obviously distribution systems, people driving cars and that. If you then look at renewables, as you go through this, you can see solar is a very small percentage. So there's actually a great opportunity. Obviously, another motivation is minimizing of greenhouse gases. People were obviously concerned about things such as global as global warming. And this is really, if you actually look at how much energy comes down onto the Earth in any one year, it's 10 to the 18 kilowatt hours, right? What's our world demand, right, is 1.3, right? It's 1/6,000th of this, 0.17 is our current world demand. And how much are we using for generating through solar? It's about 0.04%. You know, solar and the price of solar has crashed over the last couple of years. There's a number of plants now over in China and other places that are producing very cheap solar panels. So in America, your solar energy had to be below about 10 watts per kilowatt hour to be 10 watts per kilowatt hour to be economically viable. People are now installing systems, not in America, but elsewhere, at 2 to 3 cents per kilowatt hour of that. So we're on the cusp where, depending on the environment you're in, solar is a viable technology. So how does solar work? This is a silicon solar cell. This was built in one of the one of the universities I worked in at one point, UNC Charlotte. The person I worked there, they were using silicon, screen printing the contacts and other things to make the device cheaper. This is a 6-inch. This is a 6-inch solar cell. So how does a solar cell work? It's essentially a PN junction. We illuminate that PN junction with light. It creates electron hole pairs. The built-in field within this device separates out the electrons and the holes into an external circuit. So when it has light on it, it's almost looking like a battery. And it's a battery that will then cause your piece of electronics or whatever to actually light up. So one way to think of a solar cell, when you've got this piece of semiconductor material and you illuminate it, it looks like almost like a battery when it's connected to an outside circuit. So what's the advantages? You know, it's moving away from a grid system where you're generating from large power stations into a distributed process. I used to work at Georgia Tech, and this was a solar panel array that was put on top of the, I think at the time it was one of the largest arrays that went in. This was sitting on top of the student activity center there. You'll hear people talk about in silicon different generations of silicon, Gen 1, Gen 2, Gen 3. So this first generation is these very simple devices. Generation 2 is where they've actually thinned the device down to save monies. And the third gen is these concentrated devices. So essentially, when you concentrate the light on it, you end up with something where it goes from 1 sun relative to the lens to 10 suns to 100 suns or that. And rather than having a device that's 6 inches, you can scale the device down relative to how you've actually concentrated the light on it. This process of concentrating lights become more important in terms of solar systems, but then you have the costs of having this lamp on here. So it then means that if you've increased the cost here, you really want to increase the efficiency here. So what's the theoretical limit of a single junction device? And what we're going to see is the thing that limits this more than anything else, and the thing that we can actually do the most for, is to actually harvest light across the complete power spectrum of the sun. So if we take silicon, silicon has a band gap of 1.12 electron volts or so it's in the infrared. So it means that anything that's below that in energy essentially passes through the silicon material. So you can see you lose about 25%, 23% of light that just passes through the material and isn't absorbed.